Okie dokie. So I recognize that's in the reverse order of voting, but since each one of these topics kind of builds on the other one, we can do it this way around, and hopefully that leads to more clarity. But I came up with a couple examples here. 3 examples, actually, that kind of go from easy beginner pointers to more difficult, the resize memory program that we were talking about yesterday. But I wanted to step through them and see how they were working. So some of this stuff we've already done. One of them is swap. That was one of the early bits. This is print stir that we've already looked at. But I've broken these in a couple ways. So I wanted to show how they work when they were broken, and I also wanted to show what we could do to fix it. So in this program, I want to print out strings. So I've written a print string thing that loops through the string, the characters I want to print, and prints them out. So I'm going to step in here and we're going to see what happens. So we call print stir, and I've got a pointer S that points at the string that I want to print. So I check to see if S is null, and then I print out the value. And then I check to see if S is null, and I print out the value. And we see my output over here. So what's going on? I'm just hitting the first address without incrementing to the next one. Let's increment to the next one. All right, step in, print the value. Wow, that actually worked better than I thought it would. That wasn't what I intended. I was going to break it in an arbitrary way, but I think I got my order of operations wrong. But it works. It works now. This dereference is totally extraneous. I thought it was going to do something different, and then I was going to ask you guys how to fix it, but it didn't do anything different. Let me edit the code and get rid of that extraneous dereference. So this is the correct way to do this. So now we bump up the pointer every time. It's kind of interesting when we watch this that this array appears to be getting consumed. What's happening to like the word goats that was here? Let me ask that question. Why isn't that not being shown anymore? We don't have a reference to it anymore. It's true. We're moving S along from one character to the next, and we've lost our pointer to the beginning of this string. Is that a problem? Yeah, it really depends on if we need that pointer at any point in the future. It turns out for print stir, no, we don't care. Like once we're done, S is on the stack, right? S is a local variable to print stir. So after we're done, we're done. And that's totally fine. If I wanted a version of print stir that for some reason returned a pointer to the original string, now I've got a problem because S doesn't point at the original string. We would probably have to do something like this. We could make a copy of it. So now P and S will point to the same place, and now we'll manipulate P so that P bounces around, but now we can return the original string. And so here in this case, it was a problem that we were manipulating because I wanted to return a pointer to the original. So now S is going to stay pointing at goats, and P is the one that we move along. So in this case, we haven't lost our handle to the original. And I should use a smaller string. And when we get to the end, we can return that value. So it really depends on if you need that value in the future. In this example, if you incremented S, would P change since it's pointing to S? That's a great question. But let me rephrase it a little bit. So in this case, P is not pointing to S. P is pointing to the same thing that S is pointing to. Does that change the question at all if I phrase it that way? Let me back up. So right here, P isn't pointing to S. P is pointing to the same thing that S is pointing to. Exactly. It's not pointing to a pointer. It's pointing to a different thing. I could have something that pointed to S, and S is a pointer. So if I had something that pointed to it, it would be a pointer to a pointer. We could do that. I don't need it for this function, but if we run it, we can see what it would mean to actually have a pointer that pointed to S. There we go. So S and P both point at the G as usual, and here's X, another pointer. It points at S. But that's not what I wanted here. I just wanted the pointers to the string. But to rephrase your question, if I incremented the thing that P pointed at, then the thing that S pointed at would also be incremented because they point at the same thing. Let me do a quick demo of that. I need to do, because it's against the rules to change a constant string ever, I need to actually make a new one right here. So I'm going to make a new string like this, and then I'll pass that in because this will allow us to actually change that string. And then if I increment the thing that P is pointing at, then we'll see that that also increments the thing that S is pointing at because they point at the same thing. The asterisk does indicate that it's a pointer to a pointer. Basically, if you take any type in C and then you add another asterisk after that type, it becomes a pointer to whatever that type was. So if the thing was already a char pointer, add another asterisk, becomes a pointer to a char pointer. So let's check this out. P and S both point at the same thing. And then I'm going to increment the thing that P points at. And the G gets incremented to an H. So now, well, since both pointers are pointing at the thing, they both have that same value at the address they're pointing to. And now it says Hotz. It's sort of like if somebody has a PO box. There is the person that owns the PO box that's standing right there with the stuff that's in the post office box, right? But if you have the post office box number, that's almost as good. If you have the post office box number, you can go put stuff in the post office box or pull stuff out of it. That's as good as having the post office box itself. The post office box number is like a pointer to the post office box. It tells you where to go. And if I know that we're interested in post office box 12 and you know that we're interested in post office box 12, if I change the value in that post office box and then you look at it, you'll see the changed value. It's really kind of the same thing here, where both S and P are pointing to the same memory location, and one of them changes the value in that memory location, then it's just a matter of course that when the other one looks in there, they'll see the changed value. Does that make any sense? Or more sense? Less sense? Senseful. It's like truthy. It's sensey. We can have pointers all over this thing if we want. There's no rule about how many pointers you can have. There's just, let's see, I'll make a new one, Q, and we'll call that S plus 3. And S plus 4. So if I run this, I'll have all kinds of pointers into the string. There's still only just the one string with goats in it. But here we are with pointers pointing to all different parts of it. And once we have those pointers, we can dereference the pointer to change or examine what's in that particular memory location. Or we can do math to bump pointers along like we do with P++ here. Let's see, what happens if you do char pointer P equals char pointer S? This is a great question too. Or char pointer P equals, this is actually dereference S. So what do we do? All right, I'm going to ask the types question here. What type is P? Char pointer. What type is S? What type is dereference S? Char. So what we have on the left-hand side of this assignment is char pointer. What we have on the right-hand side is char. So that's a type mismatch. You can't assign a char into a char pointer. So if I try to build this thing, I think it's going to stop me. It didn't stop me. This is going to be weird. It says the pointer is garbage. Program terminated. Yeah, so that was a little bit weird. I thought it would stop me at the compilation phase. I'm certain if I give this to GCC, it's going to be like, hey. But so what really happened here when it tried to run? First of all, we assigned P to be the value that's at S. So S is pointing to the letter G. So we said P should be equal to the letter G. The letter G, of course, is something in the ASCII table, which is, let's see, let me look it up really fast. capital G is 71. So we were basically saying, I want P to point at address 71 in memory. Remember, memory is just a big array of bytes. So we were saying P points at byte number 71. And that's kind of arbitrary. And so we were like, P points at byte 71. Without warnings and stuff, C is perfectly happy. Like, okay, I'll point at byte number 71 in memory. I hope you know what you're doing. And we're like, oh yeah, we got it. And then we check and see, we look at it right here. We're like, dereference P, what's at byte 71 in memory? And at this point, the computer or the operating system is going to be like, hey, you don't have access to byte 71. You have access to like where S is and where P is and all that stuff. That's all good. But byte 71, you just made that up. That's mine. And so the OS at that point will be like, hey, crash. And that's what happens when you see things like segmentation fault. It typically means you've accessed some memory that you don't have permission to access. That was a good question. But again, if I throw this exact same code into GCC, let me see here. I don't know how to use my own shell. Control D, here we go. So there's our warning. Incompatible integer to pointer conversion. When initializing a char pointer with an expression of type char, it suggests remove the dereference. And here it's pointing out exactly where the error is. Cool. Any more ideas for what we can do to change this stuff up? I've got a couple more examples here. Yeah, it's kind of hilarious. They use the poo emoji for bad pointers in the visualizer. Why not use S? Just use S instead of making pointer P. So yeah, I could totally do that. That's the way I had it originally. But then I decided that I wanted to return a copy of the original pointer. But if I don't want to return a copy of the original pointer, then I don't care anymore. I don't need this. And I can just use S here and then stop returning it. The best case for a pointer to a pointer is if we want to modify a pointer inside a function, and we want to return that modification back to the caller. It's just like the best case for a pointer is if you want to pass in an int, say, into a function and have that function change the value that is in that int, and then have that reflected back out in the calling function, then you would have to pass a pointer to that int so that it could change the int. So it's the same thing with pointers. I can run an example of that. Let's do another example first, though. This is my swap example. So I've got X and Y. I print out what the values are. I want to swap them, and then I want to print out the values again. And here's a swap. It's got an int A and B and a temporary variable, and it does a swap with that temporary variable. So if I step through this, we see we have X and Y on the stack in main. We print out their values. we call swap, and we've got a, b, and t in swap. These are the local variables. And then we initialize them. And we see that a and b get swapped, so a is 20 and b is 10. But I haven't actually changed the values of x and y out here in main. They're still 10 and 20, the same as they've always been. So I print it out and it says x is 10, y is now 20. What do I have to do for x and y in main to be swapped? It says it is. It seems like this code didn't actually do anything. Did a lot of work up here to actually swap a and b inside the function, but x and y stayed the same. What do I have to do if I want x and y to change out here in main? We should do some pointers. If I want this function, let me step ahead again. Oops, let me step back so I get into the function. There we go. So if I want this function, swap, to be able to change these values that are out here in main, it needs to be able to access those values. And so it needs pointers to those values. Otherwise, it can't change them. Otherwise, it can only change its own local copies of these things. So let's make pointers to these values. So I want a pointer to a thing, a pointer to another thing. What else do I have to do? Exactly. It lets us do multiple returns without using the return. Because in C, you can only return one thing, so if you need to return more than one thing, then you need pointers. It pointer T well, let's see. It's the question. Do we want this to be, do we want T to be a pointer, or do we want it to not be a pointer? That dereference A, B, A. So it might be useful to remember here that we're trying to swap the values that are in A and B. Not a pointer. Let's see what happens. Not a pointer. Yes, a pointer. Let's see here. X is 10, Y is 20. We do this. We say swap. Why are my A and B pointers? Why are they garbage? Not a pointer because we want to swap the addresses associated with the values rather than swap the pointers. I might change the phrasing on that a little bit to say that we want to swap the values in the addresses rather than swap the pointers. I feel like I'm going to get a crash right here though because my A and B pointers are pointing at garbage for some reason. What do we pass in here? We said X is 10, Y is 20, and then we passed 10 and 20 into swap. So A is 10, B is 20, which probably isn't what we wanted. We wanted A to point to X, and we wanted B to point to Y. So yeah, let's change x. Let's change this expression to be a pointer to x. Address of, same as pointer. So we'll use the address of operator. Address of operator for this. Let's see what happens here. So now x is 10, y is 20. We print that out. Close this error dialog. We say swap x and y. There we go. All right. A points at x, B points at y. So with these pointers, swap now basically has access to those original variables back in main. Just like if you had the address of the PO box, you would have access to that particular PO box. Imagine you're looking at a big old wall of PO boxes. You're like, which one has X in it and which one has Y in it? Well, we know because we passed them in. We passed in those pointers, and now those pointers are in A and B. T is just an integer value. We're saying on the next line, line 7, T equals whatever B points at. So let's see, B points at Y, so T should become 20 at this point. And now on line 8, I'm saying whatever B points at should take the value of whatever A points at. So B is pointing at Y, A is pointing at X, X is 10, Y is 20, so Y should become 10 after this. And then lastly, we're saying the thing that A points at gets the value in T. A points at X, and so. And you see up here, this is all in main. Even though we're running in swap right now, we're changing values back in main. And now if we step forward again, and we print them out, we see the X and Y are now swapped. I want to do one more. So this is working. I want to do one more test with the dereference here, or with the pointer. With the pointer, I need T to point at something. So right now I've initialized a pointer T and it's not pointing at anything. I could say T points at the same thing B points at, and then we could do this. But now we're actually back to the exact same problem we had at the beginning. Here we're swapping some pointers, which is interesting, but it doesn't actually change anything back in main. So here are our pointers. A points at X, B points at Y. Here, T also points at Y now. And then I swap them around. Boy, that was a lot of drawing. It's hard to see. But basically, at this point, A is pointing at Y, and B is pointing at X. So we've changed pointers around. We've swapped the pointers, so they point, instead of A pointing at X and B pointing at Y, now A points at Y, B points at X. But that didn't really buy us anything back in main, where X is still 10 and Y is still 20. So we didn't want to swap the pointers, we wanted to swap the things that they pointed at. It might be interesting, yeah, if we were returning new pointers. We can do new pointer returns with this example. This is the resize memory example. This one's already functional, I think. But here, let's do some of this stuff and check it out. Allocate myself 20 bytes right there with malloc 20. Returns a pointer. I store that in char pointer S. And here I do a string copy to copy a string into there. So we see S is pointing at the letter P of pointers rock. And now I'm going to call our resize memory function. And I'm saying here, I want to resize the memory that's pointed to by S. Used to be 30 bytes long, because that's what used to be 30 bytes long. Used to be, I changed this at the last minute. Used to be 20 bytes long. And I want to resize it to be 5 bytes long. So I want to resize it down. So let's step in there. Here's our resize memory. First, I'll check to see if new size is 0. It's not. This is the value we passed in. It's a void pointer, because pointer to void points to anything. It's pointing at 80, which is the ASCII value of capital P of pointers rock. It's just showing us the numeric value here, though, because it's a void pointer. And that's okay. We don't need to know in here that it's a char or not. So I want to allocate enough space for my new copy of it. And there that is. New space is pointing at my new 5 bytes that I wanted. I got the old size and the new size here in local variables. I want to figure out how many bytes to copy. Remember from yesterday, if the new size was bigger, then we wanted to copy more bytes. If it was smaller, we wanted to copy fewer bytes. So since new size is smaller than the old size, we only want to copy new size bytes over, and the rest of them will just be lost. And then I'm going to call our mem copy, and we're going to pass in new space, pointer, and bytes to copy. So where we want to go, where we're copying from, and how many bytes to copy. So now we're in here. All our other pointers and stuff still exist in main, in resize memory. That's all still good. And we get more copies of those here. So destination and source point up here at our 2 arrays. And then I'm going to have char pointer variants of those, S and D, so that we can copy a byte at a time. And then this is our regular mem copy loop from yesterday, where I copy the first 5 bytes. So 80, 111, 105, 110, 116, and then we're done. And then pointer points at the older, bigger memory, but I'm done with that at this point. So I'm going to free it. And all those pointers that pointed to it, S back in main when we first mallocked it, and pointer, which is a copy of was a copy of S up here, now point at nothing because we freed it. So we can't use that anymore, but that's okay. It's freed. We're done with it. The new space isn't freed though, it's here, but I want to return a copy of this pointer back to main, otherwise we're going to lose it. So I return a copy of new space. So here's an example of returning pointers from functions. And indeed right here it says resize memory returns a void pointer. So when we come back to main, we're going to store a new space. That's going to get returned. We're going to store it in T here. So there we are. T is a char pointer. So it's showing these as characters again. And we see that we've copied the first 5 bytes. And I can print that out. I thought I could print that out. Why did the program terminate there? Oh, why? That's a good question. I should ask you. Why did the program terminate there? There's no terminator on my array. So printf is like, oh, you want me to print a string? Well, we know how that works. We print until there's a null, right? Prints P, O, I, N, T, and then it runs out of memory. It's like, hey, you can't print that. You don't have access to that. So let's fix that by just throwing a null terminator on there. Let's see, bytes to copy, free, blah, 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 scroll. So let's say I still want to copy the 5 bytes. Let's copy 5 bytes. So the new thing is 5 bytes long, but then I want to set that last byte to null, to a null terminator. What would I have to add right here to make that happen? So I just want to, it says point, I just want to overwrite the T with a null character, the null terminator. What's the C code for that? I should say I want to overwrite the T in the word point. We have a pointer to the capital P, but we don't have a pointer to the T. T plus 5 equals null. Error, L value required as left operand of assignment. What does that mean? L value. You probably think of L value in C terminology. L value means the thing that is on the left side of an assignment operator. So whatever's left of the equal sign here, it needs to be a certain type of expression that's known as an L value. And this is telling us T plus 5 is not an L value, which means it's not something you can assign into. Dereference T plus 5, how about that? So T is a pointer, and so T plus 5 is also a pointer. But we want to dereference that thing to change what it's pointing at. So this is 5 bytes down from there. Let's see if I can just skip forward quite a bit. So we return to main. Dereference T plus 5 is null. Program terminated. Why? Let's see. Here's T plus 0, T plus 1, T plus 2, T plus 3, T plus 4. T plus 5 is off the end. So what do we actually want? T plus 4. Let's do that. There are only 3 things that are hard about C programming: pointers and off by 1 errors. I'm going to skip way ahead to the end again. We return back here. Now we say T is here, so dereference T plus 4 is going to be changing the value over that letter T. Bam, there we go. We got nuked with a null terminator. Now when we print it, hey, it prints out. Of course, resize memory called malloc, so to be correct, we should call free, and then the program's done. What's another way to write dereference T plus 4? What's another way to write this expression? Array pointer equivalence. We could have totally written this as T sub 4. So both these lines, totally equivalent. That's a great question, Andrew. Does it matter where the free is, if it's in main or resize memory? Like, the question is also sort of, does the free have to happen in the same function that the malloc happened in, right? And the answer is no, the freeze can happen anywhere. When you malloc some memory, it ends up on the heap and it just stays there. It doesn't matter like which functions get called, which functions return. It stays there throughout until somebody calls free with a pointer to that thing. So once you malloc a thing, you should consider it to be there until you free. It's the only way it goes away is if you free it or if the program exits. So it doesn't actually matter where the free is, as long as you got a pointer to that thing you want to free. That was why in some of the earlier examples, we would have a string and we'd have 2 pointers to it. It was really nice to have a pointer out in main to it, but then we make a copy of the pointer when we call the function, and they both point to the same string, but main still had its copy. So that's also a good question, Carlos, because all the memory does get freed when the program exits. So since we're just exiting on line 53, do we really need to free on line 51? And the answer is no, you don't really need to. If we hadn't freed here, then the program would have exited and it would have been freed. That would have been fine. But the other answer is yes, you really should, because it's good form to have at least 1 free for every malloc that you make. So programmers, when they're looking at the code, they're like, hey, there's a malloc with no free, and it raises a flag in the back of their head. They're like, is this some oversight? Should there have been a free? Is there a free somewhere else? So by putting it there explicitly, then people reading your code can be like, oh yeah, okay, I see. We allocated here, we freed here. I'm happy. If you do char u equals dereference s, u exists on the stack, yes. Yes, let's make one right here. Sorry, char u equals dereference s. So make a character u, set it equal to the value of whatever s is pointing to, namely that capital P. Here's something that's a bit of a mental leap, but I'll say it anyway. Every variable you declare, that variable is on the stack. So even s is on the stack. See, it says right here, stack, s. The thing that s points to, that's on the heap though, that's somewhere else. So it's important to keep the differentiation between the variable s, which is itself on the stack, and the thing s points at, which is somewhere else entirely. So u, here we go, where's that line? So dereference u equals s. So yeah, so u is on the stack because all local variables are on the stack. And we've said here u gets a copy of whatever p is pointing at. U would only exist within the lifetime of this function, which is main. That's absolutely true. Here's the other thing though. S only exists for the lifetime of this function as well. Let me do another quick example here of this. What am I doing? Duplicate. So I'm going to make a new function here. Now let's do it this way. So I'm going to make a new function, and we're going to check out what exists where in this. So if I typed all that right, that was a big hurry. Sorry, I've been programming in Rust, so I did my braces wrong. So look what we have on the stack here. We have char pointer P on the stack, and then I call foo with P, and S gets to be a copy of that. So S is a char pointer here. It's a local variable to foo, so it's on the stack. It points at a thing that's out here on the heap. Once foo returns, S is gone because it was on the stack. But that thing that was on the heap here, it never went anywhere. So all local variables go on the stack even if they're pointers. It's just that the thing that they're pointing to is not necessarily on the stack. Does that make sense? So here's our local variable S, totally good. S is gone, but the thing S pointed at is not gone. Let's see, 952. And what do I want to do? Now I'm free. We kind of did that. Fork exec. I think we have time. One more example here. I'm gonna have a string here. I'll use my favorite goat string, and I want to write a function that finds the letter A in a string, and it returns a pointer to that. Except I don't want to return anything. I want to modify a pointer that's out here. So I want a pointer to the A. And what I want to do is I want to have a function, find A, and I want to be able to pass this pointer in, and I want the function to be able to change this pointer so that it points at the letter A. But I better pass in the string too. Find the A in there. So the first one is the string, and the second one is wherever the A is. And so I could write a function like this. We're just going to scan through the string. Well, dereference P is not null. Let's scan through. And if dereference P is the letter A, then great, we found it. I want to, I don't know what to call this pointer. I'm going to call it Q. I've got too many A's floating around. Then I want to remember that and have this pointer point at the letter A. And so that'll be good. We'll remember to increment our pointer this time. And if, let's see here. Well, let's just leave it at this for the moment and see what happens. I've been programming Rust. This is what happens when you change languages so frequently. All right. Oh, it is in the while loop. It's just not in the if. So S points to goats. Well, great. The A points at nothing right now. P points at goats. We're going to start our scan. Is it A? No. We'll go to the next one. There it is, A. All right. Q equals P. Why didn't, that's weird. Why didn't my Q pointer show up here? Oh, this visualizer sometimes drives me crazy. I saw it do the assignment. It did it right. Q is assigned P. Grr. This is spoiling my demo a little bit. Let me see if I can what can I do to make this happen? Right now, I'm trying to coax the visualizer into showing me what Q is pointing at. I can't get it to show me the arrow. I don't know why. Am I doing something wrong here? That's obvious. It seems like by assigning QP that they should both point at the letter A. And indeed, when I print out whatever Q is pointing at, it prints out the letter A. But I don't see my arrow. So at this point, we're going to have to use our imagination a little bit. Imagine that Q is pointing at the letter A, which it really should be. This is driving me bananas. Let's do more of them. Come on, visualizer. I know you can do it. I don't want to change the thing that, I don't want to change where Q is, I don't want to change the thing that Q is pointing at, because Q currently isn't pointing at anything. We made a variable, but it's initialized. What is this, red X? Oh yeah, this is the old one where I left off the parentheses on accident. It keeps track of the previous error, but I've added the parentheses. Come on, you show me the arrow. No, it's not gonna. All right. But Q is pointing at the letter A. I know it is because when I print it out right here, it prints out a letter A. So that's great. But the problem here is the A back in main is still pointing at nothing. We've initialized it to nothing, so it's not pointing at anything. I can even point it at something else. Whatever. Get rid of my extra stuff there. Maybe this will coax it into working. So the A points at whatever, but I want to change it to point at the letter A in goats. Boo. I cannot make it change. I'm going to mess with this later and see if I can show you a different demo at a different time, because without the Q pointing at the right thing, I know Q is not pointing at whatever at this point, but the visualizer is not showing this correctly. So the pointer-to-pointer demo is going to have to wait, I think, or I could just jump right to it. The problem is here we're only changing the local copy Q, and I want to change the A. So the short answer, if I can jump to the spoilers, is I need to pass a pointer to the A so that up here in find A, it's able to change the value back here in main. I don't want it to change just its local Q. I want it to change the one back in main. So here's where I need a pointer to a pointer. And then hopefully this, the A points at whatever, find A. All right, at least it updated Q this time. Q is now pointing to the A. It's pointing back in main. So find A now has access to the A back in main. And I can scan my string. And then I can say dereference Q equals P, which There we go. Yeah, that changed it. Let me back up one step. So the A is currently pointing at the W and whatever, but we want it to point at the A and goats. And so here we're saying, hey, change the thing that Q is pointing at to be equal to whatever P is. So P points at the A. The thing that Q is pointing at is this guy. So if I step forward, we see it changed. So this is a use case for a pointer to a pointer. And I'm sorry I couldn't visualize it in the broken case, but and it's all because Q gives us access back to the A in main. It allows us to change it. Of course, I don't stop at that point, but that's okay. And now the A points at the A and goats. A quick pointer to pointer example. I think the big takeaway from this and from the other ones is that if you want to change something back in main from a function, you need a pointer like Q right here. You need a pointer that points back to the thing in main that you want to change. But like I said, one of the main use cases for pointers is having a function that changes a value back in main or back in the caller. And that value oftentimes is just an int, in which case we have a pointer to an int. But sometimes that value is a char pointer, in which case we have a pointer to a char pointer. You mean, Brian, in terms of just one thing, you mean using return instead of a pointer to a pointer? Yep, you could totally do that. So this example in that regard is a little bit contrived because I could have just returned the value instead of used a pointer to a pointer. But there are some functions that just want pointers to things, even though they could return those things. And sometimes that's because return's already been used for something else, or sometimes it's because the thing is large and you don't want to pass or I guess pointers to things are never large. Scratch that last bit. All right. Any more questions or thoughts on any of the stuff that we went through here? Useful exercise, not useful exercise? For pointers, for me, it was all about reps. It was just do a bunch of stuff. And questions like, hey, I've got this big array and I want to change the 19th element in that array and I have a pointer to the beginning. How do I change the 19th element? Or how do I loop through every fifth element in this array? Or how do I set this element at this pointer equal to the value that's stored at the address pointed to by another pointer? That kind of thing. The visualizer is pretty awesome just because it actually shows what the things are pointing at, especially when you make a function call and you end up with two pointers to the same piece of memory. Here we've got S in main, and we've got a pointer to this. Like, there's just one copy of goats, but we can use pointers to address different parts of it. So Are parameters in a function always going to be pointers? They could be any type. So they could be pointer types, or they could just be int types or float types. It's not that they're pointers, it's that they're always copies is the thing. They're copies of whatever you pass in. So regardless of whether or not it's a constant value or a variable that you're passing in, it's just gets passed in as a copy. So here in the visualization, A should get 123. It's a copy of what we passed in here. S points inside Printster. S points at this S out here. It's a copy though. So everything here in this thing is a copy of whatever we specified down here. So can we just pass an actual string? The answer is kind of yes and no. Yes, because a string is just a char pointer, and you can pass a char pointer. And no, because a string is just a char pointer. So, and C, the concept of a string is totally loosely defined, right? It's a pointer to a char. That's basically it, with kind of a gentleman's agreement that somewhere down the line is a null character. So you can't pass all those bytes as such, but you can pass the pointer to the first one, and that's really all a string is in C. So if you wanted to pass a copy of actual bytes of the string, then you could do that by wrapping up an array inside a struct. That actually works, but because structs get passed by entire copies of structs. In higher level languages, a string would be something more sensible, like something that had a length associated with it, and functionality that prevented you from writing off the ends of strings, or functionality that would make it a no factor, that like that bug I had earlier where I was trying to print a string with no null terminator on it, it crashed. Like, you can just simply in JavaScript, you cannot do that. You can't make a string that doesn't have an end. That's not a concept that exists in JavaScript. But in C, you can make a string that doesn't have an end, and that's kind of a fault when you do it. So, is this what strings are really like under the hood? Yes, partially. So, there are all kinds of caveats and asterisks on what I'm about to say in terms of like ASCII and Unicode and stuff like that. But let's just assume that we're using ASCII. So partially, yes. Under the surface, somewhere is a sequence of bytes that's stored in a string that looks just like this. So in memory someplace, you're going to have one byte after another with your JavaScript string. But there's probably no null terminator on it. JavaScript strings keep track of their length instead. So it's sort of this very similar to how we were saying there are two ways to loop through arrays in C. You can either pass in a length to say how many bytes to do, or you can put some kind of terminator at the end. So in C, they used a terminator for strings. In JavaScript, they'll use a length for strings instead. So the actual bytes, yes, those will be in memory, but no null terminator. Instead, there will be a length associated with it. Oh yeah, we're going to get to them. I was going to take a break and then jump to the other things. But good heads up, Cameron. Let's do that 5-minute break and then launch into files and fork and exec. If that sounds good. What am I doing? Timer, that's what I'm doing. All right, all my drinks are empty. So everybody grab that coffee and let your brain think about something else entirely for 5 minutes. Here comes the roaster. All right. Catch you all in 4 minutes and 45 seconds. I don't know what happened to my rooster. Cock-a-doodle-doo. It was just dead silence. That was not the same. Oh, let's see. Let's see. One last question from me on line 12. This one right here. Is it the memory has to come from somewhere? Yes, it does. This is a good question. For this one, because S is local, a local array, I just omitted the number here. The compiler automatically put the number 6 in there because that's how many bytes goats is, plus the null terminator. So this is actually an array of 6. I just didn't write it. Because this is a local array, it goes on the stack. So it's not really like malloc. It's just space put on the stack along with all other local variables that would be in here. So if it's a local array, space for that array gets put on the stack. If it's a local pointer, space for the pointer gets put on the stack, but then when you malloc stuff to go along with it, that stuff goes out on the heap. Absolutely correct, yes. Carlos, when the function is done, the local array will be gone. Yep. Cool. All right. Let's see. File IO. File IO is what I had on there next. And I'm trying to remember from the assignment, was there something in particular about file IO that I should cover? Like, should I do it from the fopen standpoint? And were there any specific questions there? I'm happy to talk about whatever. Let's see. Let me get rid of this. Where am I? Get myself some scratch paper here. Curious about the file types. All right, the file pointer. So there are kind of two layers of stuff that we have here. One of them is the operating system layer, because the OS is going to be the one responsible for doing file I/O. It's one of its jobs. And at the operating system layer, there's system calls to do file I/O. And those system calls are things like open, read, write, and close. But open, read, write, and close are unwieldy because they have basic functionality. Read and write, they basically read a stream of bytes or write a stream of bytes. That's all. They don't have neat things like printing out numbers or things like printf can do, and so on. So what the inventors of C did was they added another layer on top of that, another layer in the C library. And this layer is the layer with file pointers in it, and fopen, and fclose, and fprintf, and fwrite. So if it starts with the letter F and it has to do with I/O, it's in the standard library. So standard io.h. Let's go ahead and write some stuff. When you call fopen, you give it a file name to open, and then you give it a mode to open it in. And the mode is like, do I want to read the file? Do I want to write the file? Do I want to append to the file? Do I want to read and write the file? Do I want to append the file and read the file? The mode can allow you to do all these sorts of things. But let's just open one for writing, which will open it to create. Now, fopen, once you have this file open, you need a way to refer to it, right? So if I want to put some bytes there, let's say I want to use fprintf to print something to the file, like hello. I need some way to refer to this file that's open. Fprintf has a question at this point: what file? you want me to print to a file. I know you want me to print to a file because F is the first letter, and that means file. But what file? I could have a bunch of files open at once. So this is where the file pointer comes in. So this is the type. File pointer is the entire type of this variable. And file is a type that is defined in standard I/O, and it's got some stuff in it. We're not quite sure what. It's what we call an opaque type. We don't know what's in that type, and we're not meant to know. We just want to use this to identify the file that we have open. So I'm going to get a file pointer back from fopen, and then we can use that file pointer to refer to the file that we want to write to. And then when I'm done, I can call fclose and close that file. So if I give this guy a run, what do I call it? File IO. Int main void. What did I just do? I must have done something dumb. What was it? I didn't save the file. That's what it was. Like, what do you mean there's no main? There's a main? Oh boy. All right, so if I run this, I'm not expecting any output on the screen because I told it to print this out to a file. And I don't get any output to the screen, but if we notice a new file has just appeared here, foo.txt, and it's got the word hello in it. So we've done that successfully. I'm going to ask you guys a pointer-related question here. FP is a pointer, so it doesn't point to anything on this first line because we haven't initialized it. But here, when we call fopen, FP suddenly points at something. Fopen has created a thing in memory and given us a pointer to that thing. The question is, if fopen created a thing in memory, when does that thing get freed? We got a pointer to it. It has to get freed sometime. But we're not calling free anywhere. That is an excellent assumption. fclose probably does it. So we don't know for sure, but in the C world, this is a safe assumption. If something returns a pointer to you, a pointer to a thing that you didn't have before, it's a safe assumption that it allocated some space for that. And then it's also a safe assumption that there's another call you should make later that effectively frees that space. And so that's probably what's happening here. fopen is probably calling malloc to give us space for whatever a file is, the capital file type, and returning one of those. And then fclose is probably freeing that thing. So the W just means open a file for writing and create that file if it doesn't exist. If we look at the man page for fopen, we see that it takes a path and a mode. Again, you can just ignore this word restrict that appears all over the place. And here we go. The argument mode points to a string beginning with one of the following letters. R open for reading, W open for writing, A open for appending. An optional plus opens the file for both reading and writing, and so on. So since the file is already open, can we do R plus? Or since it's already there? Yes, we totally could. So that would open the file for reading and writing since the file's already there, and we could read from it, and then we could also write to it. Or we could just open it for reading. Let's just open it again here. Open it for reading. Come on, if I get my comma. And then we'll do something, and then we'll close it. So we want to read some stuff out of here, and there are a couple ways to do this. fprintf, the opposite of printf has kind of historically been scanf, but there is another great function called fgets that, oh yeah, there it is, the int. fgets will read a string out of a file and store it. It needs a buffer that's already allocated to read into, and it needs a maximum size of that buffer. So I'm going to make a buffer, we'll call it, buffer is just another fancy name for string that you store stuff in. I'll make 128 bytes big, and I'll say read into this, maximum of 128 bytes, and then I'll give it the file that I want to read from. So, oops, an fclose obviously takes an argument that I've left off. So that'll read it into the buffer. That doesn't have any output, so let's print it out. Get all my quotes right there. Buffer. Okay. So we opened it for writing. Write the word hello into it. Close it. Open it for reading. Have a buffer to read stuff into. Read a line into it. Fopen. Run the right thing. There we go. Buffer is hello. Notice that there's a new line at the end of hello, which makes sense because that's what we wrote in right here. Oftentimes when you're printing out strings like this, it's nice to put quotes around them so that you can visually detect things like, oh, hey, there was a new line at the end of that. We could also open it for reading and writing. That's kind of rarer. And if I run this again, it should just be the same because we didn't actually write anything to it. But we could have. We could have read this in and then called fprintf something else. To the file pointer. To be honest, I can't remember where this is going to put it. Let's see what happens. So it read it, and then we printed something else to it. Let's have a look at foo.text. There it is. So it read up to here, and then it started writing from where it read off, or where it left off the reading. I don't know. How's this feeling? There are a bunch of different ways to write. There's fprintf, fwrite, fputs. Just like there's a bunch of different ways to read. fscanf, fread, fgets, fgetc, fputc. Yep, you can absolutely do that. Do I have something in the previous directory? Contains.py. I wonder what that is. Some stuff. All right. So yeah, I should be able to open. I don't want to overwrite it, so I'm just going to open it for reading, and we won't be able to write that. So we should be able to put in a full path here. Read the first line of contains.py in the previous directory. I guess that's the first line. Yep, sure enough. The first line is hashtag pseudocode new line. So that's what we read. You can create a new directory. This is definitely an operating system thing to do. I'm trying to remember if there's a standard library way of doing it, and I don't recall, but there is. Oh, sorry, let me look in the right section of the manual. Manual 2, make dir. There is make dir, path and a mode. So I'm not going to dig into this too much right now, but we could absolutely make another subdirectory here. It needs a mode. I'm going to gloss over this and hand wave, so ignore that for the moment. So this should make a new subdirectory. I need to include sysstat.h, it says. Let's see if that gives me what I'm after. So this is what we have in here right now. And there, we've made a new subdirectory. Is fgetS explicitly for reading the first line? Yeah, or first line or subsequent lines. It returns null when it gets to the end of a file. So if we wanted to read an entire file, here's a trick for commenting out large chunks of code. Sometimes C programmers do this, if 0 followed by end if. This works even if you have comments in there, which is nice. But we could do a loop right here. We open that thing. So while this is not null, we can do stuff. Red %s. I'm going to take the new line off because I know there's a new line in there already. So I think at this point we'll open this file. We have a buffer. We're going to read lines until we get a null back, which means end of file or error. Then I'm going to print out whatever that line was. So I think if I run this, sorry, let's get rid of our make subdirectory as well because I don't want to remake that. So here it just read individual lines of the file in a loop and printed them out. If I have a line that's longer than 128 characters, fgetS is only going to read a partial line. So this isn't a very robust thing. If I wanted to be safer, I'd make this like 8 kilobytes or something. I can also make this size of buff, so I don't have to keep changing both numbers. But now I can read lines up to 8 kilobytes long, which is much better, but not perfect. You'd probably come across files that are like maybe even a megabyte on a single line. So if you want to be able to handle that, you have to get trickier. But this is good enough for now. Can you not give buff a size? You mean above and beyond giving it the size 8,000 here? Yeah, I can't declare it without a size because fgetS expects that memory is allocated to store stuff in. So I have to allocate some kind of memory to store the results in, either with malloc or with just making it a local array like I've done here. So the OS variant of this, if I cover that, let's pull this thing out of here. Uses something called file descriptors. Let me try to remember all my, let's see, open path flags. Okay, so let's open foo.txt, and the flag is read only. I can't remember. Let's see, flags. Open file for reading only. All right. And this is in here. So check out the parallels between these two things. So here I'm writing, I'm not using the standard library. I'm just calling the operating system straight up. But here's the example where we were writing using fopen and fprintf. Here's an example. I did spell this right. Where is it? Maybe it is in systat. Where is it? Oh, file control. My mistake. That's better. Okay. So that opens the file. But then we only have a few functions at our disposal. We have read, which can read from a file descriptor, read into a buffer a certain number of bytes, and that's all. It returns the number of bytes actually read, but it doesn't read until a new line or anything like that. It just reads the number of bytes that it can, up to a maximum of this. So I could do something similar where I have my buffer. I think I commented the other one out. So then read from the file descriptor into the buffer some number of bytes, maximum. Go ahead and print those out. And then close. So you can see how it's really similar to what we did with fopen, except now the file descriptor, we call it, is just an integer. That's all. And we've opened that thing for read-only mode, so really similar to R in quotes. And then I've read some data out of it, and then I can print out that data. One catch is that I did not null terminate this. So printing it out could be bad because there's not a null terminator on there. I'm going to be kind of cheating. I'm going to initialize this entire array to 0 so that it's full of null terminators. And whatever we read will have a null terminator at the end so that I can print it out. So I think this one should go, except that I'm missing all my includes. Sys types, sys uio, I'm not even sure what that is, and Unix standard. Okay. Unused variable fp, yeah, I forgot to comment that out. Let's give it a run. So it read in my bytes, except instead of going through the standard library, we're going through the operating system directly. A little less convenient because I didn't have fgetS at my disposal. But again, the exact same concept. Open the file, allocate some resources, we get a handle back to those resources, and we can use this handle to perform actions on those resources. Oh, let's see. What's a good example of reading and writing? It's basically any time you want to save anything to disk. If you're using any application that saves anything to disk, like Photoshop or something, then Photoshop is going to use something like this if it's written in C. I'm not sure if it is. But if you want to save that image out, it's going to open a file for writing, it's going to start writing the bytes of that image out. It will have computed those bytes in memory ahead of time. Like if it wanted a JPEG, it will have encoded a JPEG in memory. And then it will start writing out those bytes. And when it's done writing them out, it'll just close the file. So it's exactly the same thing, except instead of just writing out the word hello, it's writing a bunch of bytes. But saving and loading your work off disk is the application for this, and that applies to any kind of work, whether it's the word hello or it's a 4 gigabyte Photoshop file, or if it's an MP3, you got an MP3 player, it's got to load that MP3 off disk, calls fopen, reads the data off disk, decodes it, turns it into music, that kind of thing. I would say the same. It's whatever your Python app is that needs to save data permanently. That's really the thing. I mean, you can always allocate memory, right? But as soon as the program exits, your memory is gone. If you want it permanently saved, then exec L and exec LE. That's a good question. Did I answer your question there, Cameron? I also feel like I missed something. Can you explain why it's not printing the terminal again? Linda's question. It wasn't printing in the terminal like early on, Linda, when I first ran it, it didn't print anything. It just saved to the file, right? Is that the part you're referring to? Oh, well, assuming it is. The reason it wasn't printing anything was because I wasn't printing anything to the screen. I didn't have any code in there to print anything to standard output, we call it. All I was doing was printing to a file, and that was it. So the output went to the file, but nothing went to standard output because I didn't ask for it. Let's see here. Let me back up and do this. Actually, the file's already written. Let's just read from it. Going right to it. I'm going to show you a sort of separate example. So fprintf always prints to a file. It needs a file pointer here of some kind. And so all this goes to a file. And so whatever file you opened for writing, this will go to the file and not to the screen. This, just printf by itself, this goes to the screen, typically. So I just didn't have any of these. That said, there is a file that also goes to the screen. This line is equivalent to this line. These two are exactly the same. So this goes to the screen. It's just shorthand for this, which is, hey, print to a file, but print to file, the file name standard output, which is something that you always have at your disposal. So if you ever see standard out floating around, then you know what it is. It's the screen. All right, let's jump to exec. I had an exec example that I wanted to share. So exec basically takes whatever program is running and replaces it with another program. Let me see if I can do a quick and dirty example. Is it section 3 of the man page? I was getting mixed up. Then I can explain about the E and what these suffixes mean. Path, arg0, null. All right. And this is in here. So I'm gonna I'm going to do some stuff. Hello world. We're good with this, right? Print hello world on the screen. I'm going to throw an exec in the middle of this thing. Exec LP in particular. And we'll run ls. So, will this build? Assuming exec LP works, if I've done it right, what's going to be the output of this program? Roughly. Let's go. Well, I got hello. I got the contents of my directory from ls, but world is gone. There is no world. What happened? It's almost like everything I do out here doesn't even matter. Exec replaces the program. So this was my program, but as soon as this line succeeded right here, the old file IO program was done. It was replaced with ls completely. So if exec succeeds, then anything else that was happening afterwards, that doesn't even exist anymore. So the print world, that was gone. We just took the program and we replaced it with ls. Which is kind of nuts. And not really useful, because what if I wanted to print world afterwards? There's no way to prevent exec from totally wiping out the current process. So how could I write this in such a way that exec ran and then world printed afterwards? So that exec LE thing, there's something in this process called the environment that's associated with the process, and it's basically a whole bunch of variables. If you type the word set on the command line, you will see a bunch of stuff that's in the environment. Or if you say echo $path, you'll see the path is in the environment. That's part of the environment. So with exec LE, anything that ends with E with exec means, hey, copy the environment as well over to the new process. So neither is really better. The question is, do you want like your path copied to the new process or not? Or do you want all your environment variables copied to the new process or not? And sometimes you do, and sometimes you don't. So, but for our purposes, it's not going to matter. Either way is probably fine. The P also stands for path, which means search the path for the program. So I didn't have to specify like user bin ls here or bin ls. It searched the path and it found it for me. So, but in terms of doing this so that world isn't overwritten, what should we do? What should we do so that world prints out? With the knowledge, with the knowledge that exec always blows away the current process, we should probably make a new process. So let's make a new process, and if we're the child process, then let's do this. And now the child process will be blown away. Oh, man, rust. Wrong language. The child process will be blown away. And that's fine. The parent process will still be here. Let's give this a run without the weight. I know you said put the weight in there, which is a good idea, but let's see what happens without it. Hello world, and the output appeared on a separate line after my prompt. It probably runs, well, I don't know, get a consistent output, but what's happening here is that the parent is forking this out, and then it's printing hello world and exiting, and then the child is running. Notably, the child is running after I get my prompt back, which means the parent has exited. So we can force the parent to wait for its child process to complete by putting a wait there. Wait, not H. Now we should have our, there we go. Awesome. I'm going to modify this a little bit more. What if I didn't want to run ls every time? What if we wanted to do this? Let's do something like this. Enter command, ignore this line. This is forcing this to print, even though it doesn't have a new line at the end. Then I'm going to use fgetS, and we're going to read in the command. So I'm going to read a command in from standard input. Now, this is going to read until a new line. So the new line is going to be at the end of that. I'm going to strip that new line off. I'm going to use this other function. Let's see, return values null. All right. This is in string. Check this out. I'm going to look in the command and find that new line that's at the end, and I'm going to get rid of it. So I'm going to get a pointer to the new line by using this built-in function, which looks from the end of a string in reverse to find a character. I'm going to tell it search command for a new line, please. And if it finds one, then I just want to blow it away. I just want to end the string there. So I'll overwrite the new line. Cool. So after I run this, I should have a command. Let's try it. Printf. Command is I'll just exit the program here because I don't want the rest of it to run yet. I just want to test what I just wrote. Enter command, foo bar baz. All right. So there's my command. It doesn't have a new line at the end. Perfect. Now, instead of running ls, I'm just going to run command. And then we'll wait for it. And then print world. Sure. All right. So I entered ls. The command was ls. It ran ls, and then it printed world. Let's modify this just a little bit more. Now what do we have? I've just written a tiny little shell. It'll only do one-word commands. It doesn't parse the command line very well yet. Oops, I'm stuck in cat mode now or something. Clearly I have bugs. But we've written a bare bones shell. It won't work with arguments, so like ls minus L won't work because it's trying to run this as an entire command, and really what we need to do is split that up into different pieces and use exec v probably to make it happen, and somehow get that minus L out here on the end like that. But at the guts of every shell, including bash, this is what's at the core. Read a command, fork a new process, exec that command, wait for it to finish. So everything else in the shell is just gravy on top of this. File redirection, running in the background. Like running in the background is the same as this, except you don't wait. If you want to run something in the background, you just go for it and don't wait for it to finish. So there, I didn't wait for it to finish. This ran in the background and printed out after my prompt came back. So small changes. Thoughts or questions on this fork exec stuff? Oh yeah, that F flush. So F flush works on output streams, and it basically says, hey, anything you've printed so far, I want that to appear right now. And that might not make a lot of sense. It's like, but I printed it. Why wouldn't it appear right now? It turns out that there's buffering in here that's hidden away from us. And sometimes if you print a lot of stuff with printf, it would actually wait until it had accumulated an entire line of stuff before printing anything. And I'm not sure if that's the case here. Let's try it without the F flush and see if that makes any difference. Nah, it doesn't make any difference in this case. There's probably an implied F flush in there. But F flush standard out means everything that I've called with printf, put that on the screen now if you haven't done it already, is all it means. If you ever printf something, especially something without a new line at the end, and it doesn't appear on the screen, then you'll want to flush the output buffer. Actually, let me try this. Let's go to sleep for 2 seconds. After that, I'll print it out, go to sleep for 2 seconds, and then, yeah, see, it doesn't print anything yet. So when I ran that, I called printf immediately, but no output happened because there was no new line at the end of it. If I really want to force the output to happen before this process goes to sleep, then I have to put the F flush in there. Another interesting thing is that you can run bash from within bash. It'll give you a new shell. Then you can exit this one and get back to the old one. Oops, not LSSH. You can run this. Shoot. Sorry, one more time. I can run that again. Now I've got 2 copies of the shell. So I'm running a shell and a shell. But I have not written an exit command, so I can't exit from my shells. I could have just added a new line as well. Yeah. Right up here, put our sleep in. So that would cause it to print right away. But now my cursor's on the next line. I didn't want it down there. That's the only real difference. Yeah, you totally could. It'd be a lot more code than I have here, but yes. Oh, speaking of that, somebody asked what my opinion of Lua was. I remember, right? I've never programmed in Lua. We used it a lot at Activision when I worked there, but people who were working on the level logic used it, and that wasn't part of my stuff. But I hear it's a really easy language to embed, and it's certainly popular in games. Yeah, games, oftentimes you don't want your level people needing to write stuff in C++ because it's a pain. So they'll embed a language within the game, like Lua, and then they can write the stuff in Lua, which is far less crashy. It won't crash like C++ does. You don't want your game to crash. Yeah, ages ago, I worked at Activision at a studio called Z-Axis. The best game I have my name on got pretty well panned. It was the X-Men 3 movie game for PlayStation and Xbox. I worked on Wolverine, so all the Wolverine action was me. People said Wolverine was very, very boring to play because all he did was punch and punch and punch and punch and punch. And every time we tried to do something different, Marvel would come to us and be like, Wolverine doesn't do that. We're like, yes, Wolverine doesn't do anything. He just punches. People are going to hate it. The game also had Iceman in there and Nightcrawler. Nightcrawler was awesome. If you watch the X-Men 3 movie from way back, whenever that was, there's a scene at the beginning where Nightcrawler busts into the Oval Office, and we used that exact movie scene to model gameplay after. And the dude, Chris March, one of my coworkers who worked on that part of the game, he did such a good job. It plays so good. It's the X-Men 3 movie game that came out in, I'm going to say like 05 or 06 or something. I'll see if I can find something on YouTube for you. I'll post that. I think I still have a shrink wrap copy floating around someplace. Certainly after programming it, I did not want to play it anymore. Imagine playing the same game over and over and over again for like 3 years. All right, gang. It's after 11, so I'm going to let everybody split here. But if you have more questions as you're hacking on stuff today, please throw them in the channel. Like I've said so many times, this stuff is really hard, and we expect that there are tons of questions. And because the material is so tough, it's hard for us to just come up here and be like, hey, we're going to talk about X, Y, and Z, and use that to get full coverage of everybody's questions. So when you ask questions of the PMs or me, it really helps us narrow down into one of the subtopics that we have to talk about. There's, in a way, there's like more information here than we can ever cover in almost a lifetime. So we pick and choose, but then as necessary, we definitely want to explore little avenues out there to help you understand it better. So keep the questions coming, and everybody will be happier. And again, it's a lot of it's the reps. If you're not getting it, don't feel bad about that. Just keep on pushing and trying stuff, seeing what works, what doesn't work, figuring out why. It'll be great. All right, gang. Have a good lunch or a brown bag that I've eaten into already. And I'll see you on the help channels. Have fun.